So let's put everything we've learned, really in all of mathematics ever, but ideally, and emphasis on the calculus part, into analyzing graphs of functions. Up until calculus, all we knew how to do was really find intercepts, find sort of general shapes, but now with the help of the derivative and the second derivative, of course, we can really kind of fuller or have a fuller understanding of a curve. So let's just like put everything together, including the first derivative test, second derivative test, everything we've ever learned to analyze and sketch the graph of functions of these sorts. So to start off, I want to attack this with all of the algebra. So start by finding intercepts and domain. Okay, so to find the domain, we just think if there's any problems with this function. In other words, are we ever taking square roots of negative numbers? And are we ever dividing by 0? So we are clearly doing neither of that. Indeed, this is simply a polynomial. So therefore, we have the domain of our function is simply the real numbers, except we're only concerned about this function over -3 to 5. So I guess we can really only look at this function over that closed domain. So instead of that, I'm actually going to say the domain of f is from -3 to 5. So we have a nice full domain here, no holes in the graph over this particular interval. Find intercepts. So let's start with x-intercepts. That would mean that we set f of x equal to 0, and we solve for x, and that clearly tells us that we ask ourselves, what's going to make this 0? Well, if x is equal to -2, or if x is equal to 4, that makes this 0. So we know our function crosses the x-axis at those values. If you know something about these squares here, and I hope you do, we know that it actually bounces off the x-axis at both of these values. So that's really crucial. To find y-intercept, we know there's only one because this is indeed a function that we set x equal to 0. And that would be 2 squared times -4 squared. And that's insane. Okay, so what is that? That's going to be 2 to the 6th, which is 64. Okay, so we have x-intercepts, we have y-intercepts. That's all important. But now we kind of want to start attacking this with respect to calculus. I think that's everything we got in terms of algebra here. I guess we could take limits, but we're only concerned about this particular region. So I guess what we could do is see how high this function is at the endpoints, because that doesn't require calculus. So let's do f of -3. That is going to be a problem. Geez. So what is that? -1 squared. It's not that bad. -7 squared. So that's going to be the same thing as 49. And we have f of 5, that's going to be the same thing as 7 squared. Oh, interesting. Which is 49. Okay. So we have this maximum value of 49, and we have these two x-intercepts, and we have a y-intercept. So we're off to a good start. Then I'll say this, then do calculus. All right, so starting to do calculus, what we want to do is take the derivative. Start with the first derivative. Taking the derivative of this function, what you could do, if you want, you can multiply that nonsense out, but what I'm going to do is the product rule and the chain rule. So that'll be 2 times x plus 2 times x minus 4 squared plus x plus 2 squared times 2 times x minus 4. So that was the product rule and the chain rule. That's going to be the same thing in cleaning things up. It looks like I have both of these terms here, having a 2, an x plus 2, and an x minus 4. So I'm going to factor that out. all that's left will be 1x minus 4 in this part right here. So that's going to be x minus 4. And then 1x plus 2 in this part right here. So that'll be plus x plus 2. Cleaning this up, that's going to be a 2 times x plus 2 times x minus 4 times, okay, so what is that? 2x minus 2. And of course that simplifies to 4 times x plus 2 times x minus 4 times x minus 1. All right, so therefore, to find critical points, set f prime of x equal to 0. Well, first of all, you should ask yourself, does this ever not exist? This is also a polynomial. We're never dividing by 0, and we are never taking square roots. So we know the only critical points will be when f prime of x is equal to 0. That's important to bring up. And of course, that gives us our critical points. We're simply asking what is going to make this polynomial equal to 0. Well, we have to simply ask what's going to make each of these individual factors equal to 0 because of the zero product rule. That gives us our critical points in increasing order of -2, 1, and 4. So those are all of our critical points. And those are all inside our region, so that's -3 to 5. So these are all of our critical points. Now, we want to see, so all we did so far was found critical points. This is huge. Now let's start using those tests. So let's start using the increasing, decreasing, and first derivative test to see if these yield maxima, minima, or neither. So let's see how that works. First derivative test. How that works is I set up a number line and use the regions. So we're only concerned from -3 to 5. And then I want to place all of our critical points. These are all points where I know my first derivative is equal to 0. And I'm wondering if they're minima or maximas. So I have -2. That's a critical point. I have 1, that's a critical point, and I have 4, that's a critical point. So what I test is numbers in between these values, okay? So I want to choose a number in between to start off with -3 and -2. So how about -2.5? And then what I do is I want to see what the first derivative looks like at that value. If I plug in -2.5 into all of these and it results in something positive, that means my function is increasing. So let's see that work. I'm going to set up, notice I have 3 parentheses. This is my first derivative. That's f prime of x. I want to see if my first derivative is positive or negative. Because remember, if the first derivative is positive, that means my original function is increasing. That's what the increasing, decreasing test says. And if I ever change from positive to negative, then I have a local maximum. Well, let's just see it. So I'm going to set up 3 parentheses. Plugging -2.5 in this guy right here, that's going to be something negative. Plugging -2.5 in this guy right here, that's also going to be something negative. And last but not least, -2.5 in this guy right here. Oh, shoot, that's negative. Resulting in a negative. 3 negatives make a negative. And therefore, my function is decreasing. So what I just used was what I call the ID test. So I could say this. By increasing, decreasing test, I am decreasing. Let's do it again. This time I want to test something in this region right here. So that there's an obvious choice. Let's test 0. Set up my parentheses. Plugging 0 into my derivative here. Where's my derivative? Right here. That'll be obviously positive, negative, negative. That's going to result in a positive. And therefore, by ID test, I am increasing. So I'm increasing here. And therefore, now what I just learned something new. That tells me by the first derivative test that I have a local minimum. Notice I'm going from down to or I'm going from decreasing to increasing, which means that must be a local minimum. So I don't know. Let's see the best way to explain that. Therefore, first derivative test says local minimum. That's what that says. I keep going with testing points. Let's grab something in here. Okay, so let's test 2. So 2 is going to be positive, then negative, then positive, which is, of course, negative. And therefore, by the increasing decreasing test, that tells me that I am decreasing. If I have a negative slope, that's what that says. We have negative slope. And also by the first derivative test, I'm changing from increasing to decreasing. Therefore, first derivative test says, so if I'm going from increasing to decreasing, that says local maximum. All right. So let me add that into my picture. I am now decreasing in this region. We have one more to check. Let's check 4. 4.5. Let's test 4.5. And that will be, I believe it's positive, then positive, then positive. But let's double check which will make a positive. It's hard to keep everything in frame. Yep. Plugging 4 in here, or 4.5, excuse me. 4.5, positive, positive, positive. Yep. And of course, therefore, by the increasing decreasing test, we know we are increasing right there. And that change from decreasing to increasing, gosh, too many arrows. The first derivative test says local, I always have to think about it. So I'm decreasing to increasing. Obviously, that means minimum, local minimum. Hopefully, this first derivative test and the increasing decreasing test really should say, or should be intuitive. So what we just found is I'm increasing right here. So overall, what we just said is local min at, or I'll say local minimums at, okay, what minimums did we collect? From decreasing to increasing, we collected minimums. Okay, so, oh, look at the chart. This is much more helpful. Local minimums at -2 at that critical point, and at 4, and local max, there's only one, at 1, because we go from increasing to decreasing there. All right, and all of these are critical points. Okay, to see the actual minimum, you simply see what these guys are. F of -2, I'm pretty sure that's going to be, oh, it's a 0, so that's 0. And 4 is a 0 too. So it has local minimums and x intercepts. And let's see what this local maximum is. F of 1 is equal to, where's my function? Oh my gosh, where's this function? Oh, here we go. So staring right here, f of 1, that's going to be 3 squared times 1, 9. Cool. F of 1 is equal to 9, and that's a local maximum. All right. So that is my local maximum value. I have the value at 1 is equal to 9, and I have 2 local minimums at -2, or local minimums of 0 at -2 and 4. And I have, it looks like we already have discovered our global maximum. Our global maximum is 49, and that occurs precisely at -3 and 5, which are the endpoints of our domain in question. So next up, we kind of just take this test and do it again, except for the second derivative. Okay, that might be a mess. Oh, geez. So, okay, so here's my first derivative. And I want to do all this game again except with the second derivative. So f prime of x is equal to 4 times x minus 1 times x minus 4 times x plus 2, I believe. Okay, I awkwardly used the commutative property. And I'm going to use a cheat. There's a famous product rule. The derivative of a times b times c is equal to a times b times c prime plus a times b prime times c plus a prime times b times c. And it's simply using the product rule twice, but I'm going to use that right here to take the derivative of the derivative, so the second derivative of x. And indeed, we are looking for points of inflection here. So that's going to be 4 times x minus 1 times x minus 4 times the derivative of this thing, but that's just 1, plus x minus 1 times the derivative of this thing, but that's just 1, times this thing, x plus 2, plus the derivative of this thing, which is 1, times this thing times this thing. Again, I'm using this yellow rule, extended product rule. So that'll be plus x minus 4 times x plus 2. That's fun. So this equals 4 times x squared minus 5x plus 4 plus x squared plus x minus 2 plus x squared minus 2x minus 8. This is the same thing as 4. How many x squareds we got? 1, 2, 3. 3x squared. Gathering x terms, minus 5, so minus 6x. Then we have plus 4 minus 2, plus 4 minus 8, that's minus 6. All right, 3 comes out, so that'll give me 12 times x squared minus 2x minus 2. Okay, and to find points of inflection, we set that second derivative, well, potential points of inflection, equal to 0. That tells us x is equal to 2 plus or minus the square root of 4 minus 4 times negative 2, all divided by 2. That's the same thing as, okay, so we'll have a 1 plus or minus the square root of 3. That's what I'm getting. All right, so those are the x values of potential points of inflection. To see if they actually are points of inflection, what we got to do is set up a sign chart. So we have 1 minus the square root of 3 and 1 plus the square root of 3. And if concavity changes, in other words, if this thing changes sign, if you know anything about parabolas, you already know that this is going to change sign nicely from here to here and to here, but I'll just show all the work. If this thing changes sign, then we will have points of inflection. So let's see. Remember, our domain is from negative 3 to 5. Root 3 is about 1.7. So 5 is over on this side. Let's test. Negative 3, so shoot, let's go negative 2.9. Well, okay, so I can just do negative 2. Like I said, root 3 is 1.7-ish. It's less than root 4, which is 2. So I can do negative 2. Plugging negative 2 into this guy right here, it's going to be 4. I can do it like this. 4 squared, or 4 plus 4 minus 2. And again, I just plugged negative 2 into this thing. And remember, it's times this positive 12. I only care if it's positive or negative here. That is going to be positive. And therefore, concave up. That's called the concavity test. So I can do this, concave up, and then let's test 0. 0 is in between here because this is root 3 is certainly bigger than 1. So testing 0, plugging 0 into this guy right here, that's clearly negative. Negative 2, because this is going to result in negative 2, is less than 0. Therefore, concave down. So these are both because of the concavity test. So to reference everything, I'll say this. Because concavity test. This is also because concavity test. I'll do CC test. Concavity test. And because of this swap from up to down means therefore point of inflection by definition. So that's really huge. So we are now concave down over this region. 1 plus root 3 is going to be about 2.7. So let's try 3. Let's test 3. So again, we're putting 3 into this function. That's going to be 9 minus 6 minus 2, which is bigger than 0, and therefore concave up. And we have another point of inflection. So changing from concave down to concave up means therefore point of inflection. And this is the concavity test that we are using. What's getting us these yellow loops, concave up or concave down, is the concavity test. And seeing that this switches tells us that it's a point of inflection. Okay, very good. So what we just concluded, points of inflection at x equals 1 plus or minus the square root of 3. Those are the two x values of the points of inflection. And I don't think I'm ever going to have you find the y values of points of inflection, but we have everything we need to set up our curve, to graph our curve. So what we've collected is critical points. Slope is 0 at -2, 1, and 4. We have global maximums at -3 and 5, the endpoints of our domain, and those maximum values are 49. We have a local maximum at 1, a local minimum at -2 and 4, and those grays the x-axis. We saw that the outputs of our function there is 0, and we have the output of our function at the local maximum is 9, and we have points of inflection at 1 plus or minus root 3. So I know our function is always positive. Our interesting points are -3. That's the end of our interest. That's the end of our point of interest. We have -2, I believe, was a critical point. Where are critical points? Yep, 1. 1 is a critical point. I believe 4 was a critical point. And we had 5 was the end of the point in question. So we know what we have 0 slope at these critical points at -2, 1, and 4. We have 0 slope. And we also have these interesting points of inflection. It's going to be 1 minus root 3. That's like -0.7. So there's 1 right here. 1 minus the square root of 3. That's where we're changing concavity. We have 1 plus the square root of 3. That's going to be like 2.7. So here's 2 here. Let's go around here. 1 plus the square root of 3. And here's what our curve looks like. Starts at -3, 49. Global maximum. Scoots down to a local minimum of -2. 0 slope right there. Concave up over this entire region, ladies and gents. Notice that from -3 to 1 minus root 3, we are concave up. And then we see a point of inflection right here. And we change from being concave up to concave down. We have a local maximum at 1. That local maximum value is going to be at 1, 9. We are still concave down, point of inflection here. I'll bet you it's the same height. Where we change from being concave down to concave up. And we have a local minimum right here, derivative 0. We better have a horizontal tangent line right here. And then we scoot all the way back up to that same local maximum, or excuse me, global maximum of 49 right here. So that's going to be 5, comma, 49. Nice, we got a nice W-looking curve right here. So to be clear, critical point at -2, at 1, and at 4, and we better have horizontal tangent lines. Yep, we sure do. We collected that we had points of inflection at the x value of the point of inflection. So I should say this. The actual point of inflection is a point on the curve. So we should technically find, if we want to actually have the point of inflection, we should find the y value, but it's too exhausting, and also who cares? A calculator can do that. Those occur, the changes in concavity occur at 1 minus root 3 and 1 plus root 3. Notice if we made a tangent line, the curve should exist on either side of the tangent line. Same thing here, if it truly is a point of inflection. And that's pretty much it. So that was a nice collection of everything we've done. We did a lot of calculus, did a lot of algebra, everything we know for a singular curve. And that's what I'm expecting. You will have a question on your exam coming up where I'm pretty much asking you to do all this, collect all. Oh, I guess one more thing. Sometimes a textbook will ask you for intervals of increase and intervals of decrease. And that really should have happened when we did the sign chart for our first derivative. So f is increasing because of the ID test. Forgot to mention this. F is increasing over -3 to -2. And we want to include this, the endpoints, because the derivative is negative over the open interval. So the ID test that says that the function itself is increasing. Oh, I'm sorry, that should say decreasing. F is decreasing. I can read the pink arrow properly. Over this one and over this closed interval. So that would be 1 to 4. And then we would say f is increasing over, let's see, we got -2 to 1 and over 4 to 5. All right. So that's like a good collection of all the knowledge we can pull from a single function. That was important. Let's try it again. That took half an hour. That's absolutely nuts. All right. So this one might be a little bit more streamlined or less streamlined. I don't know. Okay. So first, I always suggest attack it with algebra. So let's do the same thing with this. Do all things algebra. So first off, I'm noticing that this function, we have a much larger function or interval of interest here, and that's the real numbers. We want to say that the domain of this function, g, that's going to be all real numbers other than 2. So we have a vertical asymptote at 2. That's something we should recall from Algebra 2, or maybe pre-calculus. We have x-intercepts. We set g of x equal to 0. That would imply that x squared minus 2x plus 4 is equal to 0. And that would imply that our x-intercepts are non-existent, because this says x squared minus 2x plus 1 plus 3 is equal to 0. And that would imply that x minus 1 squared plus 3 is equal to 0, which is a contradiction. That doesn't make any sense. That thing's never equal to 0. Okay, so there are none. Y-intercept. g of 0 is equal to 4 over negative 2, which is going to be negative 2. Again, just letting all these x's equal 0. So our function crosses the y-axis at negative 2. And I'm thinking that's everything we got. This is the big thing we just learned. We have a vertical asymptote at x equals 2. So that's important to remember. Like, for instance, we might find that our critical point, we might see or accidentally think we have a critical point at negative 2, but that's impossible. Critical points always occur within the domain of the function in question. So I think that's all the algebra we can do. So let's do some calculus. Oh, actually, no, I don't think that's all the algebra we can do. Notice, yeah, let's pause with the calculus, relax with calculus. That should be our last resort here. We can do polynomial long division. So I think g of x is the same thing as x squared minus 2x plus 4, all divided by x minus 2. But that's the same thing as what I'm going to do is simply force this denominator to show up in the numerator and then clean up mess. In other words, I clearly lied if I left it like that, but I'm going to multiply this thing by something so that an x squared shows up. And that's clearly going to be x. And then when I distribute this x to both of these guys, I'll have an x squared and then minus a 2x. So both of these things are picked up. But in order to make this a complete thought here, I would have to add that 2. And this is the same thing as x plus 4 over x minus 2. And that's because we have already assumed that x does not equal 2. All right, so this is really my function g. Then we do calculus. Oh, I guess I should say this is, I don't know if you remember this, but this is what I call a slant asymptote. Once your function on top is a degree less than the function on the bottom, or the expression on top is a degree less than the expression on the bottom, then you have completed your division, and this is what I call a slant asymptote. So far, here's what our curve is going to look like. This is not going to be my official curve, but I have a vertical asymptote at x equals 2, slant asymptote of y equals x. That's where this comes from. And I also have intercepts, so I know my curve crosses right here, which means that my curve is sort of going to hug this like this, and it's like a hyperbola looking thing. And it's also going to do this. Notice it does not cross the x-axis. We concluded this curve never crosses the x-axis. But here's the cool thing. We can figure out what these points are, where they have horizontal tangents all of a sudden, because we have the tools of calculus. Recall that you were not able to find the range of such a function because you didn't have calculus. When you learned about this function in algebra, we were able to pick up everything about it except for the range, as well as these local minimums and local maximums. But notice that the derivative of this function is equal to 0 there, which means we can certainly find those values using calculus. Okay, so then g prime. So what I'm going to say is then do calculus. G prime of x is equal to, I'm going to take the derivative of this one. Let's see, that's going to be 1 minus 4 divided by x minus 2 squared. Just check my work. Use the quotient rule or the power rule, whatever the heck you would like. And then to find when we have critical points, we first ask when this doesn't exist. Okay, so this doesn't exist only when x equals 2. But x equals 2 is not even in the domain of my function. So I extract that, or I neglect that as a critical point. That's really important. And then I set g prime of x equal to 0. And that would imply that 4 over x minus 2 squared is equal to 1. And in order for that to happen, that implies that either x is equal to 0 or x is equal to, what would that be, 4? I'm just wondering what's going to make this denominator equal to 4. Negative 2 squared is going to be 4, so that means x is equal to 0. And 4 minus 2 is 2. 2 squared is equal to 4, so that would work as well. So these are our critical points. I'll just do this. Critical points, 0 and 4. All right. And let's see if there's minimums and maximums there. That does mean this guy was wrong, because this is actually where the maximum occurs. So my curve actually looks something like this. And this guy right here occurs at 4. And this horizontal tangent line does not occur in any sort of positive x value. It occurs at 0. So that's why this calculus is so powerful. It tells us that the maximum of the curve actually happens on the y-axis. That's what we just discovered. Well, first of all, hopefully it's a maximum. We now can prove that it's a maximum. Let's check these critical points. We have 0. We have a huge hole in our graph at 2, so we will have to check on both sides of that. Then we have 4. So to test our derivative, g prime of x, we just need to choose something in this region. I'll choose -1. We have 1 minus 4 divided by 9, and that is certainly bigger than 0, which implies g is increasing in this region. And let's check it. Anything in between here and here. Let's check 1. Let's test 1. Oops. Let's test 1. We'll have 1 minus 4. Again, what I'm doing is I'm plugging this into my derivative function up here. It's out of frame. It looks something like that. Which is less than 0, which implies g is decreasing. And the first derivative test therefore says max, local max, at x equals 0. Okay. So why? Because our function goes from increasing to decreasing, which means we must have a local maximum right there. And that is because of the first derivative tests. I'm not just telling you that. All right, let's try something in here. Let's try 1. That's going to be the same thing. Let's test. Oh, I already tested 1. I'm sorry. Let me test 3. I'll have 1 minus 4. That's going to be the same thing, which is still less than 0, which implies g is decreasing. So the first derivative test wouldn't have said anything anyways. I don't have a local minimum or a local maximum here. But I can't have a local minimum or a maximum because 2 is not a critical point. 2 is not even in the domain of my function. So in either case, I know that there's no local extrema that occur at 2. Let's try 1 billion. It's going to be 1 minus tiny, which is bigger than 0, which implies g is increasing. So here we go. We have an increasing function past 4, which means that, therefore, the first derivative test says local minimum at x equals 4. And that's because this is the critical point, this is the critical point. And this is going to give us a really good idea for what our graph looks like. And if we were to guess, I bet if we took the derivative again, we will see that our function is concave down over the entire interval from -infinity to 2, and concave up over the entire interval from 2 to positive infinity. And we really kind of knew that before we started, but let's see if this concavity test works. So taking the second derivative, g double prime, okay, so that's going to be 8 divided by x minus 2 cubed. Setting this equal to 0 to find possible points of inflection. What we have is x minus 2. Well, Wait a second. This is never equal to 0. So I have to check the regions on both sides of the domain. That's right. This implies that, well, what this implies is 8 is equal to 0, which is ridiculous. And so we really just need to check concavity on both regions in the domain. This guy is always positive? Is that true? No. I mean, this is just a funky looking thing. As the second derivative has a vertical asymptote at 2. So let's test something back here. On this side of 2, 0, then G prime, double prime of 0, is clearly negative. In fact, equal to -1. And therefore, concave down. And I'll do an extra thing here to use, because I haven't used the second derivative test. But I'll do that in a second. Concave down. And let's try this. Let's test something on the other side of 2, 3. G double prime of 3 is equal to 8. Simply plugging 3 into this function right here. And that's positive, which implies concave up. And like I said, you might be tempted, oh, sweet, we switched concavity, which means that 2 must be an inflection point. But no, that's wrong, because 2 is not even in the domain of the original function. That's why I kind of put this pathological example out here. This 2 is really causing problems. It's not even in the domain of the function, which means we do not care about it. So therefore, no inflection points. Even though we swapped concavity, we do not have an inflection point. All right, and we're going to get to a place where we can really sketch our curve. But what I'm going to do first is show you how to use the second derivative test, because I rarely use the second derivative test, because to me, the first derivative test is plenty. And you have the sign chart right there ready to go. Like this is telling us everything we need to know in terms of local extrema. But if you have, the second derivative test says, second derivative test, if f prime of something is equal to 0 and f double prime of something is negative, that implies local maximum. So we already found a local maximum at 0. So let's see if that works. And we know, notice f prime of 0 is equal to 0. And let's do f double prime of 0. That is going to equal 8 divided by -2 cubed, and that's the same thing as 8 divided by -8, which is -1, which is less than 0. And therefore, just to see an example of how the second derivative test works, what the second derivative test is 0, x equals 0, yields a local max. Like I said, we already knew that with the first derivative test, but this is a different way to sort of think about it. And we also know, notice, I'm pretty sure, what was the other critical point? 4. F prime of 4 is also equal to 0, and f double prime of 4, that's going to equal 8 divided by 4 minus 2 cubed, which is equal to 8 divided by 8, which is equal to 1, which is positive, which means we are concave up, looks something like this, and you have a derivative that has a 0 slope, which means that we must have a local minimum. X equals 4 yields a local minimum. And both of those, what I just did is I used the second derivative test just to see an example of that guy. All right, so these are very involved questions. We're really kind of dissecting this function to death, but I think we have everything we need. Notice that this function, because the limit of this function as x approaches infinity is equal to infinity, there are no global maximums. It gets arbitrarily large. In a similar fashion, there are also no global minimums, because it gets arbitrarily small. As x goes to negative infinity, this function approaches negative infinity as well. Also, you could have taken the limit as x approaches 2 from either side. You would have concluded the same thing. But I think we have everything we need. No inflection points, sad. But we do have critical points. Collecting everything about this function. Algebra told us vertical asymptote at x equals 2. Horizontal slant asymptote of y equals x. And I'm running out of room. Let me try this again. I'll do it like this, make it a little bit closer. And I have critical points here, 0. Y-intercept here of 2. And I have a critical point, okay, so this is x equals 2. I have a critical point here, double that length, of 4. And here's negative 2. Okay, and I think that's all I need. My function looks exactly like this. Horizontal tangent line, boom, critical local maximum because of the first derivative test. Shoots off to negative infinity right there. And I have a local minimum right here, horizontal tangent line, again shoots off to infinity. It looks like it's about to cross that line, but it's not. And of course, we can discover the height of this function. Maybe let's do that real quick. So what was the original function? I think it was, this is g. G of 4 is equal to 4 squared minus 2 times 4 plus 4, all divided by 4 minus 2. So, geez, that's a lot of 4s. We got 4 times 4 minus 2 plus 1, all divided by 2. So that's the same thing as 2 times 3, which is 6. There you go. All right, so that looks good. Notice that our function is concave down over this entire interval. That's what we expected. Concave up over this entire interval. Still no inflection point because we have this vertical asymptote, which cuts our entire function into different branches. We've kind of exhausted this to death. What's so cool here, though, is these points were undiscoverable up until calculus. We now have tools to see the exact values here. This is the point 4, 6. We did not know that prior to this. This is the point 0, negative 2. That's a negative 2. And there we go. So that's a good example. I had a few more in mind, but I really want to keep these videos short. For homework, there you go. Punt it to homework. Look like a great teacher here. Try these. I might do them in lecture on Saturday.